of our FDP and advanced topics in control system. I'm delighted to welcome all of you to the final day of this FDP, where we have explored several emerging and impactful ideas over the past few days. Each session so far has provided valuable insights into modern control strategies, estimation techniques, and optimization methods. Unfortunately, due to an important institutional function, Dr. R.K. Munje is unable to be with us in this session. Nevertheless, we are confident that today's session will be equally enriching and intellectually stimulating. We look forward to your active participation and engaging discussions throughout the session. So, let me introduce today's eminent speaker. It's my pleasure to introduce my colleague and our next speaker, Dr. Anand Kumar, Assistant Professor in Department of Electrical Engineering at KKWIEER Institute of Engineering, Education and Research, Nasik. Dr. Anand Kumar completed his BE in Electrical and Electronics Engineering from Oriental Institute of Science and Technology, Bhopal in 2013 and obtained his MTech and PhD degrees from the National Institute of Technology, Patna in 2017 and 2021 respectively. He brings diverse academic experience, having served as at prestigious institutions including SVNIT Surat, NIT Hamirpur, YBN University Ranchi, and Buddha Institute of Technology Gaya before joining KKWIEER Institute in August 2024. Dr. Anand Kumar has published research contributions in reputed journals and conferences, including 3 SEI index journals, 2 Scopus index journals, 3 IEEE conference papers, and a book chapter. He is also a recipient of the Best Paper Award at ICEF EET 2020. His research focuses on advanced controller design technologies for the frequency and voltage stabilization in power systems, particularly under nonlinearities and uncertainties, an area of significant importance in modern power grids. Today, he will be delivering a talk on Metaheuristic optimized sliding mode control for frequency stabilization under uncertainty and nonlinearities. Participants, please join me in extending a warm welcome to Dr. Anand Kumar. We are looking forward to an insightful and technically enriching session. Over to you, sir.
Okay, thank you, Mary ma'am, for introductions, and good afternoon to everyone. I am Dr. Anand Kumar and currently assistant professor in Department of Electrical Engineering, KKWIEER Institute of Engineering Education and Research, and it is my great pleasure to be part of the 4th International's FDP on the advanced topic in control system organized by the KKWIEER Institute of Engineering Education Research, and I am very thankful to Merin ma'am and our HOD R.K. Munje sir to give me opportunity to share some research in the field of control designs for the power system analysis like the frequency and voltage regulation. Just here I want to share my slides. Okay, thank you. I hope my voice is clear and the slide is visible to all of you.
Yes, sir.
Okay. And today is the 4th International FDP on the advanced topic in the control system, that is already going on from the 9th February 2026 to 14th Feb 2026, and today my topic is the Metaheuristic optimized sliding mode control for frequency stabilization under the uncertainty and the nonlinearity. And the outline of the presentation is the first of all we have to know about the what is the process control systems, and thereafter we have to go for the process control design technique, which technique we are using for the any systems for process control system, and thereafter we have to discuss about the basics of the sliding mode controls, and and thereafter we have discussed the sliding mode control design methods and the implementation of the sliding mode controller to LFC systems. We have designed the sliding mode controller for the load frequency controller control of the power system analysis, and we have tuned the load frequency controller sliding mode controller parameter using the particle sum optimization and the Gray-Wolf optimization technique, and we have discussed the simulation and result analysis of various case study using the sliding mode control. And last section is here conclusion and future scope. First of all, we have to go with the process control system. Process, what is a process? Process is a complex arrangement of different units in order to achieve a certain goals, and the process is modeled as a first order plus dead time, second order plus dead time, and for the higher order system it may be the LFC system, non-reheat system, that is the third order, and for the reheat we are using, that is the fourth order, and we can use in any systems. Process is a arrangement of different unit, and the process are modeled and grouped in a different category so that their analysis, design and simulation become easier. And here is this is your process variable, output variables, and this is the reference. Here we are f of s is use the set point reference, so that if there is any noise in the set point references, then that can be eliminated. And we have to focus on design of the controllers, that is your C of s, and this is your disturbance that is coming in your systems. And this is the basic classic unity negative feedback control systems. And our objective of the control design technique, we have to design any controllers to keep the process variable as close as to the desired specification, whatever we want to design for that. If there is any reference with respect to reference, we have to eliminate the disturbance coming in our system, we can eliminate. Main objective of the control system to design and the second is we have to design the controller where the process variable, output variable of the system follow the variation in set point. If there is a set variation is coming in our set point and in any disturbance or uncertainty in the system, then we have to eliminate all these things, and we have to maintain the set point response, and we have to get the desired set point response. And third one is we have designed the controller sufficiently to robust, so that if there is any parameter change in the systems, and so that we can get the desired value. And the performance are analyzed through the observation with respect to set point response. We have to design here with respect to load disturbance response. That is the basics of the load frequency control, why we have to go for the controller designs. Next one is in this section we have to discuss the various process control design technique. That one is first of all is the classical feedback configuration, that is we have already discussed, that is the unity negative feedback control. A structure is there, and where the process is there, controller is there, and for that process we want to control with respect to reference and with respect to the disturbance, that is the classical feedback configuration. Another one is second one is 2 degree of freedoms classical configuration, in which we have to design the controllers with respect to set point and with respect to reference independently. There is no effect of the disturbance when we have to design the controller with respect to reference, and there is no problem, there is nothing. We have to design the controller independently. Similarly, parallel controller structure is also similar to the 2 degree freedoms controller classical configuration. These are the structures of any method we have to design, like the PID controllers, PIDA, cascade, anything we want to design the controller. These are the structures. Fourth one is the cascade control techniques. Cascade controller structures is there, that is the cascade controller structure for the any system we have to design. And the fifth one is your 2 degree freedom IMC controller structure, in which we have to design the set point response with respect to IMC control techniques. And for the disturbance rejection we use the separate control technique, that is your load disturbance controllers for rejection of the disturbance coming in the systems. And the fifth one is the sliding mode control. Above all, these are the structures of the systems. for which we have to design some controllers. There is a one controller is there, there is one structure is there, and there is how can we tune the controller, that is the approach. By using, we have to design the PID and PID controller by using approach, that is your direct synthesis approach, that is a classical approach techniques. Yeah, you can design the PID using Ziegler-Nicholas, Cohen-Kuhn, yeah, any method you are using, that is your approach. How can you tune that controllers in the system? And we have to above 5 is your structures, and again if you have to design some complex control systems, then you have to go with the optimization techniques. Before optimization technique is not available, if it's not in our system, then we have to use the classical control technique and various methods available in our research. We have to go for that. So first of all, you have to understand what is the structure of the system, what is the controller of the system, and which method we are using to find tune the any controllers. And next one, just all these works I have already done in these fields, that's why I am explaining all these things. That is actually today my topic is mainly sliding mode controller design. How can we design the sliding mode control for any systems? But we have to know these things. And first of all, we have to discuss the parallel control structures. That is, the parallel control structure is this is your actual process model, this is the your nominal process models, with both are the equals, approx equals. There is some changes in the system, and we have to design in parallel structures. This structure is like that. These are the output of the system, this is your change in frequency, and this is your reference signals. And we have to design it's like that. When we have to design change in frequency with respect to reference, then we have to go for the set point controller, that is your KC1. When you have designed your systems with change in frequency with respect to the disturbance in the system, then we have to go with the, that is your KC2, that is your low disturbance controllers. So that's why this is also named as 2 degree of freedom control structures, and that is the ability to tune the controller to get the desired set point response and the low disturbance response independently for these systems. And we have tuned this controller, set point controller and the low disturbance controller, using the direct synthesis approach. This direct synthesis approach very well discussed by the Lloyd Raja sir in the first day of first sessions, and they have already know the what is the, when we have to design using the direct synthesis approach, you have to match the actual process characteristics of the actual system with respect to desired characteristics of the systems at the specified or at the desired poles. And using this you can tune the controllers whatever you want to design at the low frequency point, because at the low frequency point the response are same. And we have to find the closed loop response change in frequency for this system, figure number 2. Then we have to get the change in frequency R into M is the actual process, KC1 1 plus Mn into KC1s, and the 1 plus Mn KC2 plus 1 plus Ma KC2. And this under the nominal condition we have assumed that the actual process model is equal to nominal process models, and when Ma is equal to Mn, then in equation 1 this part is cancelled out, and the overall equation 1 will become like a change in frequency is equal to R into Mn KC1 1 plus Mn KC1 plus Mn nominal process model 1 plus KC2 and D. Then we have clearly seen that the change in frequency with respect to reference, then we have to go with the set point controller KC1, and when we have to tune our system with respect to disturbance, then we have to go with the KC2, that is your low disturbance controllers. And this is your parallel control structure. This is also similar like a 2 degree freedoms, where we can tune the set point and low disturbance controller independently. Next one is IMC controller. This is the IMC controller technique basics, where the Yes, next one is the structure of IMC controller, in which that is your actual process model, this is your nominal process model, and we have to, due to using this, we have to reject the disturbance in the systems fastly using the IMC controller. This is the structure, this is the transfer function for these systems that is available in the, this structure is taken from the reference number 4 in the reference sections. And the next one is the structure of 2-degree freedom IMC controllers, in which this is your actual process model and this is the nominal process model, and in which we can tune the set point response with respect to change in outputs using the IMC controller, and whatever be the disturbance occur in our system, we can eliminate using the disturbance controller SD. This is the transfer functions we have to find with respect to y with respect to r, that is this in equation 4, and for perfect nominal model we have to equate the actual process model with the nominal model, and equation will become, and for the set point response we can tune using the IMC controller, for the disturbance response we can tune using the load disturbance controller SD. And the next one is we have designed PID and PIDA controllers, and this is the structure of PID controller, and we have used the low pass filter here to eliminate the noise that is present in our systems, and this is the equations for the PID controllers, and this is the structure of the PIDA controllers. We have designed these two controllers using the direct synthesis approach for the frequency regulation in power system, and we have observed that here that due to using the derivative control in our system, there is noise present in our systems, and so that we can use the low pass filter so that we can eliminate noise of the derivative filters and the double derivative filter in the system. All these methods we have all, that is tuned using the direct synthesis approach for the frequency regulation in systems. And the next one we have to come now, our main topic is the sliding mode controller design for frequency regulation in our systems, and we have to know about what is the sliding mode control techniques. Sliding mode control technique is derived from the variable structure control, which is originally studied by the Utkin, and that in 1997. In 1997,
Sorry.
that is, yes, there is any questions? Okay, actually the first time the sliding mode controller that is given by Utkin in 1997. Before that, and that time, that is also known as they have named as a variable structure controls, and that is this, and they have the state that the first step in the sliding mode control, we have seen that define the sliding surface. First of all, we have defined the sliding surface that represent the desired closed loop behavior of the system, for which we have to designing that controllers, and for that they are using the integral differentials equations, characteristic equations, that is the dy dt plus lambda to raise the power n integration of 0 to 2 et dt, that is the sliding surface equations that is defined. And the second step is to design the sliding mode controller, is that to design a controller that drive the system output until it reaches the sliding surface and keep it there, and we have to reach the sliding surface and keep it there. If there is any disturbance occur in our system, then they have come to the reaching surface to sliding surface and keep it there. Second step, for that we have to go for the controller, design controller, and that is the reaching and the sliding surface. And once the ST is reached, sliding surface is reached, it is desired to make the derivative of the sliding surface is equal to 0, so as to make the constant value of ST, and error is equal to 0. Error is equal to maintain the trajectory sliding on the surface. And whatever I am explaining, that is very well explained by the Lavre sir before 2 days, and sir has already derived all the derivations, and they have discussed in more details each and every things, and they have also guided him regarding the which optimization technique is better to tune that for SMC, sliding mode controllers. And the next one is that this type of control methodology has ability to deal with the time varying non-linear systems very well, compared to the classical PID control techniques, where somewhere we are not able to control our system using the classical control technique. That's why we are using the sliding mode and any model predictive control like the robust controller designs for the unstable and the complex systems. And thus in sliding mode control law, we have, there is two part is there, that is a continuous control part and the discontinuous control part is there. There is two part is there, and the continuous control part, in the continuous control part, that is used to make the system to reach the sliding surface and a stable. But main problem of the sliding mode controller is that the chattering problems. When there is a uncertainty, a non-linear coming in our systems, then the sliding mode controller, that is moving from the reaching to the sliding surface very fast, and that is the chattering problem is coming in our system, that is removed by the discontinuous part. That I will explain in later slides. And next one is this is the structure of the sliding mode controller. This is the plant, this is disturbance, this is the output response, and this is the reference. And in the last slide, this continuous control part is the function of output variable x and the reference r and the error in the system, that is e. Continuous control part is the function of this. And first of all, we have to design the sliding mode controller for the third order system. Generally there is many method is available in our systems. They have designed for the first order plus delay times and the second order systems, and many of the papers I have studied, they have used the paid approximations for the designing of the sliding mode control and any approximation technique to reduce the order of the systems. During reducing the order of the systems, you have seen there is some little change, very small changes in our systems also occur, but we have to design the transfer function for the third order system that can be written as this is the third order system, T1s plus 1, T2s plus 1 and T3s plus 1, and all of you have to know how can we design. And for this is your x by u output with respect to the reference. Here u we have written here, and the sliding surface equation is this. Actually there is yes, first of all we have to understand how can we design the sliding modes. Again there is some issue. Now first of all we have to design the sliding mode controller for the third order system, and in this equation number 8 it is derived from the integral differential characteristic equations that I have already told that is the sliding surface that is equal to the dy dt plus lambda to the power n and integration of 0 to infinity error of the system into dt. From that we have to design. The sliding surface is very important for any system, whatever you have to design for that system. And this is also known as sliding mode control is also known as also known as non-smooth PID controllers, because we have designed that system for the third order system. That's why double derivative is coming in this system, this sliding surface. But if you have designed for the second order system, then it's look like a PID control, that is known as non-smooth PID control. There is a derivative part is there, K2 into dy dt of Et, and proportional part of that with respect to error, and the integration part of that. So that's why that is also known as the non-smooth PID controllers. And first of all, we have to design the sliding surface according to the order of the systems, and we have to written like that. Here in the sliding, voice is clear to all of you? Okay, next is the, that's why this sliding surface we can say it is the PIDA controllers, yeah, double derivative controller, because there is double derivative term is there. And the next one, first of all, we have to design the according to system behavior, we have to select the sliding surface, and next one, from that sliding surface, from equation number 7 we can find it. Equation number 7 we can write like this, by the cross multiplication of the equation number 7. And here we can T1, T2, T3 is the time constant of the systems, and the x triple derivative of the xt, and the T1, T2, and that is equation number 1. Here k into ut is there for the third order differential equation. And the equation number 8, from equation number 8 we can write is, this is the derivative of the and from the equation number 7, equation number 8, we can write this sliding surface like that. S derivative of sliding surface is equal to k1 into e triple dot t, and the k2 into double derivative of error, and the k3 into derivative of error, and the k4 into et equal to 0. For make the to design the controller, we have to set the derivative of the sliding surface to 0, equal to 0, and we have taken error in our system is equal to reference minus the output response, that is RT minus ET. And from using equation number 9, these equations, and equation number 11, we have to put this ET is equal to here, and we have to find the, from here we can use the equation number 9 and 11 in equation number 10, and we can get this. When you have to put the ET, you have to find the value is equal to 0, and you have to double derivative of ET. It means when you have to derive the constant term, reference term, then equal to 0. That's why that will become a minus term here, that is the minus k by t1, t2, t3, because when you have equated to 0, then that will come to the next side. The minus k divided by t1 to et, and we have to derive using this equation number 12. That is very, very important. All these steps are very, very important, and all these steps are explained in the Camacho paper 2004, and the another one paper that is the Rogers and Camacho paper in 2004 and 2017 papers. That paper is very, very important paper for these derivations for the second order system. They have designed the controller for the first order plus delay time and the second order systems. And next one, we have to come with there is a sliding mode controllers, and in first slide we have explained that there is a control line, there is two parties there. One is the continuous control part is there, another one is the discontinuous control part. And in continuous control part we have already find there is a 4 tuning parameter is there. In the actual definitions, there is a lambda is the tuning parameters, and here we have convert lambda into 4, k1, k2, k3 and k4. That is the coefficient of this system. This is the tuning. Another one is the discontinuous control part. There is a kd and the st divided by mod of st by delta t, that is derived from the Lyapunov function, that is derived in the Laurentian presentation. They have derived very well, and that discontinuous control part, in which there is two tuning parameter, KD and delta are using the delta are the tuning parameter. We have tuned using the particle sum optimization, and we have also used the Gray-Wolf optimization techniques. And the discontinuous part incorporate a non-linear element that represent the switching element of the controller. And there is a switching element, and the KD is a gain, which is the tuning parameter responsible for the reaching mode. We have to reach the reaching modes, and delta is the tuning parameter used to reduce the shattering problems. To reach the sliding surface, we have to remove the shattering problems. And already sir has explained that there is a sigmoid function and the hyperbolic tangent function is used to eliminate the shattering problems occur in the sliding mode control. And they have also designed in the Mehta and the Camacho papers in this, that is all that is given in the reference number 6 and 7. And we have the 6 tuning parameter here for third order systems, that we can tune the tuning parameter using, we have used the Gray-Wolf optimization technique and the particle sum optimization techniques. And we have used the objective function is the integral square error of the error signals, that is taken as an objective function. Here integral square error is the e square t dt. And for the eliminating the high, if you want to suppress the large error in your system, then you have to go best suited for the integral square error. And if there is a small error that you want to, then you have to select objective function as an integral absolute error. When with respect to time in your system error is increasing, then you have to use the integral time absolute error, integral time square error, you can use it according to your application. And for your system complexity and your design analysis, you can select the integral square error. And I am very happy in the Labrasser lecture is that they have select the objective functions, and they have the different weightage for the square error and the integral time absolute errors they have using. That is the very good way and to select the objective functions. And our next is the whatever we have learned in the previous slides, that is how can we design the sliding mode controller for the third order system. We can implement in the load frequency controller of the power system. This system is your third order systems, that is non-linear non-reheat single area power systems. And here is the transfer function of this system with respect to changing frequency with respect to reference unit u. And that is GP is your generator and load transfer function, turbine transfer function, and the governor transfer function. And the characteristic is this one GP divided by this. And this transfer function can be written as, after the solving this equation, you can get this, that is your generator and plant gain, and the TP your generator load time constant, turbine time governor, and the KP and R is the speed regulation of the generator and load. As the load is increasing your system, the rotor speed of the generator is decreasing, and that is the omega equations for the continuous control part. How can we design it? Continuous control part of the using the sliding mode control that we have used the previous slides. How can we go with that? Here these are the equations. From this the UCT is obtained, and the x of t we are getting, and the next term is minus from that. And when we have to error is RT minus XT, and you have put here in this equation and equate to 0, then it will become this, that is equation number 12. And from this is your UCT, this is your UCT, this is your continuous control part of the systems. And from that we can find the continuous control part of the systems is like that. And we have know that the resulting sliding mode controllers in which there is a continuous and discontinuous control part, and this is the discontinuous control part. KD and delta is your for the discontinuous part, and we have to tune for the remove the chattering problems coming in our systems. And here we have used the objective function, that is integral square error for the single area systems. For the multi area power system we can use the multiple objective function, that is your change in frequency 1 del f1 square and del f2 square and dot dot this. And for the Thailand power we have used this. Using 18 and 19 is the objective function for the single area and multi-area power systems. And this is the equation for the multi-area power system. Here this is your primary control loop and this is your secondary control loop. In secondary control loop, this is your sliding mode controller we have using. This is your area controller error. If there is any change in load in area 1, then we can supply power from 2, and that is sensed by Thailand power, and that is given to the system. And in the designing process, this is a bias factor, that is 1 by Ra plus Di. This is damping load coefficients of the system. And for the designing the multi-area power systems, controller design for the multi-area system, just we have to consider the bias factor, we have to multiply in the resulting power system for the single area power system. And we have used as a nonlinearity in our system, in that is explained in 5.9, and that is the generation rate constant, that is we have used in our systems, because as the load demand is increasing, in that case your frequency is drooping very fastly, and governor give more streams to the turbines and try to generate more power to maintain the frequency. During that times the turbine blade may break and the system may damage. That's why in the practical power system we have used the generation rate constant as a nonlinearity and the governor deadband also, if to maintain our system for reliable power system. We have used these two type of nonlinearity in our systems. And there is one anti-GRC scheme, that is the way TAN, they have used that schemes to overcome the problem of GRC. Whatever be the problem is coming from the GRC, that can be eliminated using anti-GRC schemes that we have used in the PID and PID controller schemes. But here we have not used the anti-GRC control techniques to overcome the nonlinearity in our systems. And the next one is these are the two tunings sliding mode controls using the particle sum optimization and the gray wolf optimization technique we have used. And these are the steps we are using for that optimization techniques. First of all, the set parameter of the POC. Initially we have to initial population of the particle with position and velocity we have to choose it, and the initial fitness of the each particle we have find it, and select the position based, which one is the best in that position. And overall, whatever be the number of population we have selected, from that we can select the global best in the system. And we have to set the number of iteration count for the getting the optimal value of the variables, and update the velocity and position of each particles. And we have to evaluate the position based and global based. If we will get the position based and the global based in the whatever we have to set the maximum iteration, that is 30-50, and from that we can get optimal value, our system is respond well, then that is okay. If not, then we have to go with the next iteration, and we have to change the global and position based. We have to use to tune the controllers for the sliding mode controller, that is K1, K2, K3, K4 and the KD and delta. And this is the simples and simples optimization techniques. Another one, we have to go with which one is the better, then we have to apply for the same system we have to apply the another optimization techniques, that is the gray wolf optimization technique, in which we have also, first of all, we have to initialize the parameter population size, maximum number of iteration, define the initial cost functions, and generate the initial populations randomly, and calculate the fitness of the alpha, beta and delta. And for each wolf we have to update the position of the current wolf and get updated position, and we have to update the value of alpha, beta and delta. And if we get the optimal value, then we can stop, and then otherwise we have to go with the another iterations. And another thing is that, and whatever we have designs, we can implement it in the that is our single area power systems with the non-reheat turbines we have taken, and that is from 8. And this is the droop characteristics and the generators time constant and the gain and the turbine and the governor time constant. And using the gray wolf optimizations, we have obtained the tuning parameter K1, K2, K3, K4 like that. This is the parameter of the KD and delta is like that, and there is another, when using the PSO we have used this after the tuning. And for the to take the controller performance, we have used the load disturbance in our system, that is your 1 pu, that is 0.01 at t equal to 1 system, t equal to 1 second, and our response is like that. When so in that case we can see that the our sliding mode controller response we have designed using the Gray-Wolf optimization technique, and in that case our the frequency deviation is very small and that will settle very fastly. And similarly second one is the best result that is given by our particle sum optimization, and Gray-Wolf optimization is the much better and fast than the particle sum optimizations. And the third one is the Anwar and Pan's paper, we have compared our result, and the Saxena and Hote sir we have to compare our results for the case study ones. And next one is these are the comparison performance analysis for the case study one, that is these are the peak value we have obtained in the frequency deviations, that is 1 into 10 minus 3, that is very small, and 1.3 and 3.39 and the 9.02. Similarly settling time to settle the within the 2% of the area bands, and that is the 1.12 seconds and 1.7, and these are the parameters, and we have to also settle very fastly compared to others too using this. And the Gray-Wolf optimizations value is much better than others, and similarly integral square error is also very less compared to others, and absolute error we have to find it, that is less, and integral time absolute errors. And we have to check how much improvement in the peak value with respect to this 9, and that is this, how much the improvement that is taken. Again we have to take in the another second non-reheat systems, and we have designed the controller using the controller using the Gray-Wolf optimized PSU. Data is this, and the disturbance applied at t equal to 0.01 pu 1 pu and at t equal to 1 second. That is a similar case, and we have obtained here also. Again we have seen that the result is much improved than the others methods, and this is the case study 2. Here we have to compare with the Pradhan and Manji and Anwar and Pan paper. And the second another case study analysis of the case study 2 is that here also we can see in the better performance in terms of the peak value, settling time, integral square errors, and the absolute errors. And the third one is the non-reheat for the single area power systems. Again here that is same thing, we have tuned the controller using the GWO, and we can see that if the system is changing, according to that our controller tuning parameter may change and the response may be different. And here in this paper and the Gundu's paper also this system is taken, and their response is frequency deviation is very high, and when we have to design using the sliding mode controller, then we can clearly see that the response is much better and improved than the others two methods. And this is the analysis. Here huge improvement in our peak value, settling time, integral square error, integral absolute error, and integral time absolute errors. And the next one is that is the non-linear. When we have to apply the non-linear in the single area power system, then we can see that the systems turn to in unstable mode, not stable, and that is the turbine with the GRC. Here we have used the generation rate constant, that is the value of the GRC is the 0.1 pu per minute, that is the 0.0017 pu. We have applied here in these systems for the generation rate constant for the turbines. And when we have used the tuning parameters, we have find the sliding mode controller and tuning parameter K1, K2, K3, K4, KD and delta. We have using the GWA is this, and the using PSO is this, and we have used this, and we can see the difference. What is the difference when using the Gray-Wolf optimization technique with GRC and without GRC? we have compared the results, and that is the non-linear. In the non-linear system also our the controllers and that work very well. Here is the frequency division for the case study 4, that is with GRC, and here the with GRC deviation is more, and without GRC you can see here the deviation is less. If GRC is not using our system, deviation is less, and when we have to use the GRC, then oscillation increases, but still our system is performing well with the non-linearity, we can say it here. Similarly with the PSO also we can get the good result. So that's why we can say that our system will work in the non-linear system also. Another thing, we have to go with the two area power systems with the non-reheat turbines, that is the this, in which we have taken the 6 cases in the two area power system under case study 4. That is when we have to take in the 0.1 pu step load in area 1, when we have to take the 0.1 pu step load in area 2, and the area 1 area 2 undergo the 0.1 pu step load simultaneously. दोनों में हम same load we can apply, then we have to check it. Another thing, when we have applied the perturbation in the system, means there is some changes, more changes in our system. Sometimes our turbines time constant may increase by 50% yet decrease by 50%. Similarly the tie line power also increase by 50%, decrease by 50%. Tie line power increase by 92% and minus 92%. In that case our system, a sliding mode controller, will work or not, that we have to study in case study 5D when the 0.1 pu step load in area 1. Another, in case 5E, we have to study that the when we have to apply the 0.1 pu step load in area 1 and the random step load in area 2, when we have apply that case, what is the results, all these things. And here for the two area power system, we have design and controller parameter is that K1 K2 value is this we have used in the two area power system. Same controller for the both systems we have used. And response, here we have seen that there is a huge improvement, and Kangdilu paper we have compared for that analysis, and here we can see that the improvement is much better and the frequency deviation is very less, around minus this, and this one blue is one the Grey-Wolf optimizations and the PSO. Here the little difference when we have used the PSO, a small better performance by the Grey-Wolf optimizations than the PSO and the Kangdilu we have observed here. And that is the frequency deviation in area 1 and area 2, that is, and for the case 5A, that is the tie line powers exchange in the systems. For case study 2 we have seen that here also everywhere you have seen that the Grey-Wolf optimization technique is performance is much better than PSO. In a similar way, you can say that you can also use the some other optimization techniques that will respond better, maybe change. And same thing we have here in the case study 2, 0.0 pu step load in area 2 we have taken. In that case also we have similar result. We have seen that the optimization using the GW and PSO is improved and compared to the Kangdilu it also. And air frequency deviation in area 2 is this in figure number 18. Again we have seen that for the tie line power also, when the step load in area 2 we have taken it. And another one, when we have to go with the both area 1 and area 2 with the 0.1 pu lead, then the little more deviations will occur, and but still our system and respond better than others in the frequency 1 and area controller error 1. The response is there. And when you have applied this is the interesting, when we have applied the 50% perturbation in the governor time constant with the 0.1 pu step load in area 1, in that case when with nominal governor time constant, then this is the blue one response, that is the nominal governor time constant we have taken. When you have increased the 50% in your governor time constant, that is one red one, that deviation is little increase but still within the range. And similar with, we have checked with the particle sum optimization technique also. In that case, with nominals a small more compared to this deviations, and when we have used the 50% increment still within the range, so that our system is, when we have to performing for the uncertainty system, anything, then the perturbation in our system, then our controller will work efficiently. Similarly, we have taken in the 50% change in the tile and power exchange in our system, then our system also responded very well. And here the both in the case similar result we have seen here. Blue line, that is the nominal tile and power, and the with the 50% increment still same, little difference is there, but that is not much more effect on our system. Similar thing we have checked with the PSO also, that is also almost similar. And next one is the, when we have to go with the 92% perturbation in tile and power, then still small deviation is there, and that is okay with that. And when in the last case 5e, we have considered the 0.1 pu step load in area 1. In area 1 we have to fix the load at 0.1 pu, and for the area 2 we have considered the random loadings, as we have to increase the load 0.1 pu to 0. Increase the loads in the area 2, we have to increase 0.05 pu. Again we have to go with the 0.09 pu, and then again we have to go with the 0.15 pu, and then reduce. He is reducing the system loads in the area 2. Again we have to reduce much, and when we have to apply the random loading in your system, then your system will respond fast or not, we have to check using the random loading patterns. And next one, here we have seen that in the first we have to increase the load, then we have seen the decreases in frequency, change in frequency as the load increases in area 2. This response we have seen, and here the settle very fastly. You can see here the Gray-Wolf optimization and PSO will settle very fastly. Again we have to increase the loads, then decrease in frequency, then increase load, decrease in frequency occur in our systems, and the settle. And again we have to reduce the system, then frequency changes occur, increase, change in frequency, increase, here the reduce, here increase. Then again we have settle the system very fastly, here we can see it. And again we have to reduce, then we can similar patterns of the result you can see here also. This is the change in frequency in area 1, this is the change in frequency in area 2. Next one is the tile and power, that is also when we have applied the random loading pattern in our systems. Next one we have to go with the 4 area power systems for these systems, and there is a parameter of the sliding mode controllers for each area is different. Here this is the controller parameter for each area, and these are using the PSO we are getting this. And for this we have checked the change in frequency in each area 1, area 2, and area 3 and area 4. And here observe that this is blue one is the frequency deviation using the Gray-Wolf optimization technique, and the orange one is the PSO and the chi-idol. And here we have seen that using the PSO and Gray-Wolf optimization technique, and the frequency deviation is better compared to others. Using the chi-idol we have used here, and these are in all cases we have seen the better performance and improvement seen in each area. And similarly we have go with the tile and power exchange in each area. We can see here result, here we can clearly see that the performance is settled within the desired value within the times and very fastly using the GWA and PSO in tile and power in 1, and tile and power in area 2, and tile and power in area 3 and 4 we have observed here. These are the 3 case studies, 6 case study we have taken here. And the conclusion is that in the sliding mode control designs for the LFC is presented, and tuning parameter of the controller is proposed using the particle sum optimization and the Gray-Wolf optimization technique, and we have applied the controllers for the single area, 2 area, and 4 area power systems is considered compared against the latest controller design methods, and the frequency response show a huge improvement in the peak overshoot and the settling times. And our sliding mode controls we can also apply for the any higher order system, and before that, and we can also extend this controllers will work very well for the renewable energy like the wind energy, photovoltaic, and the hydro energy system, and we can also apply for the cyber attack. And we have seen that the sliding mode controller is will work in the robotics systems, aerospace, and any unstable and that reject the disturbance, uncertainty, and non-linearity very fastly. And these are the selected we have references paper we have used here. uh, we have taken the non-linearity from the TAN papers, and the Utkin, this is the 1997. This paper is here, I think by mistake written in 1977, but 1997 first time sliding mode controller is published. That is the variable control structure for the sliding mode controllers. That is a very important paper is in the sliding mode control. And the another paper is the Kamcho and the this one. Thank you all.
Thank you so much, sir. Dear participants, now it's open for questions. If you have any questions, you can unmute yourself and raise the questions. Otherwise, you can type your questions in the chat box.
Hello.
Sir.
Hello.
Voice is coming, sir. Hello, sir. Yes, sir.
Sir, you have compared the Grey Wolf optimizer.
Yes,
That is
yes.
GW and PSO. Okay.
Yes, yes, sir. Yes, sir.
So, in case of PSO,
Yes,
whether
sir.
you have been used the classical PSO or some modified PSO over there?
Yes, sir. I have used the classical PSO, and that PSO program we have designed.
Inertia weight method you have been used over there.
Yes, yes, sir. I am just using the weight we have selected, and we have used that the classical PSO techniques here, not the modified PSO, sir.
Okay. And now your plant is the power system plant. Okay.
Yes, yes, sir. Yes, sir.
So, sir, how will you quantify the non-linearities and disturbances in your real-time applications?
Yes, sir. I have this controller technique we have not used in the real-time application, but we have whatever we have designed in the direct synthesis approach.
I know, sir.
Yes, yes.
You won't use in a real-time manner or real-time
Yes, sir.
fashion.
Yes.
But just
Yes.
logically, how will you quantify the non-linearities and disturbances in the power system? Your plant.
Yes, what we have the design that systems, that is we have not the during the designing parameter. Now we have not considered the non-linearity, and we have designed that systems controllers in here, and that controller will work in the non-linear also for the non-linears. Here we have designed for these systems, for third order system, for these systems.
Okay. And for most of applications, any either PID it is there or some sliding mode controller it is there, or any other S2 infinity controller it is there.
Yes.
Normally, the bandwidth of controller is third times the plant. Okay.
Yes.
So in your case, what is your bandwidth of your controller?
Sir, in this sliding mode controller technique, we have not used the bandwidth, but during the direct synthesis approach, we have used the bandwidth and the tuning the lambda. We have considered here, but here we have not considered, sir.
No, sir. your plant is having bandwidth. Okay. So
Yes.
every controller and every plant it is having bandwidth. Very first thing.
Yes. Yes.
Huh. So theoretically we are taking the controller bandwidth as a 3 times the plant bandwidth. Obviously, sir.
Okay.
Because controller has to process the plant.
Yes.
Yes or
Yes.
no?
Yes. Yes.
So, huh. So practically, as your load frequency arrangement it is there. So
Yes.
practically, how much controller bandwidth you have been considered over there?
Sir, actually, we have not analyzed in terms of bandwidth for the during the controller designs. So actually, we have not. During the direct sensing approach, we have considered the bandwidth at low
Hmm.
frequency points, and at the low frequency point, we have seen that the frequency response and the characteristic of the two systems same. And at
Huh.
that point, we have designed the lambda for that system, and we can tune the controllers there. In that case, we have taken the bandwidth
Huh.
complete analysis during the designing process, but here we have not considered, sir.
Okay, okay, sir. Very
Yes.
nice presentation, Dr.
Yes, sir.
Anand.
I have learned many things from your presentation, sir. Also,
Yeah.
sir. Very nice by
Uh,
you, sir.
yes,
And
sir.
yes, okay.
Very nice presentation, sir.
Okay, sir.
Yes.
Thank you, sir.
Okay.
Thank you so much, sir. Participants, any other questions from your side?
Hello.
Hello, sir.
Yes.
Sir, you're
But
audible, please.
okay. Thickness packet in the nonlinear model is
Hello, sir. Your voice is very less, sir. Can you speak?
the how does the boundary the
Yes. Yes, sir.
how does boundary layer the thickness packet in the nonlinear sliding mode concept?
How does we select the boundary conditions? Actually,
Yeah, I mean
question,
boundary layer the thickness
sir. Actually, voice is not clear. I'm not understanding. Boundary layer. Just I'm listening here. Hello, sir. Can you in chat box you can write your.
Deep, sir? Yes. Sir, question is here. How does boundary layer thickness affect in nonlinear SMC?
Sir, when we have designed boundary layer thickness affect the nonlinearity problems, and during the that will also create the chattering problems, and that's why we have considered during the designing the discontinuous control part. We have select, sir. Using that we can solve the nonlinear issue, nonlinear sliding mode controller design technique.
I hope there is no further questions from participant side. So we sincerely thank Dr. Anand Kumar for delivering an insightful session. We deeply appreciate his time, effort, and willingness to share his knowledge with us. I thank all of the participants to actively participate in this sessions. Thank you so much, sir. Uh, as we are having our next two invited experts. They are currently engaged due to some exam commitments and due to some medical reasons. So because of that, this session will be marked as the conclusion of our FDP. We sincerely appreciate your understanding and cooperation in this regard. Before we conclude the session, I would like to invite a few participants to share their reflections and learning experiences from this enriching 6 days FDP. So your feedback will be truly helpful for us to understand the impact of the session. So I would like to invite few of the participants to give a feedback on this 6 days FDP. You can raise your hands or you can unmute yourself and please give us a feedback. Dr. Rajshekhar, are you available? Dr. Nisha? Dr. Meghnathan, are you available? Dr. Seema Patil, madam? Anyone, please unmute and give a feedback on this FDPs. It will be truly encouraging for us. Sanjeev Deshpande, sir. Soumya, madam, are you available?
Ma'am,
Yes, sir. Please proceed.
myself, Professor Javed Patel from Vidyalankar Institute of Technology. Am I audible?
Yes, yes, sir. You're audible. Please come.
Actually, I have gone through all our sessions of FDP. They were great, great learning. This time we got some international speakers also. So great learning from those speakers also. We'll take a lot from this particular FDP. And thank you very much for organizing such great FDP. And we are looking forward for such FDP from KKWIEER and workshops related to control system. Thank you very much, and big thank from Vidyalankar Institute of Technology.
Thank you so much, sir. Your feedback is so valuable for us. Like we got a feedback from Rajeshwari Kannan, madam. Like she is also
evening, ma'am.
appreciating. Yes, ma'am. Please proceed.
Yeah, good evening, ma'am. So good evening, all. So first of all, I would like to thank the coordinators for conducting this FTP on advanced control systems. Okay, in a very good manner, without having much delay between the sessions. And anyway, congratulations. And again, we could get a very clear picture on the nutshell in almost in the advanced control system area. And those who are doing the research also have enriched from all the sessions, and it's a great experience, learning experience. For that's all from my end, ma'am. Thank you.
Thank you so much, madam. That is really great appreciation for us. Anyone else, participants?
Myself, Dr. Meghanathan, ma'am.
Yes, sir. Please.
Ma'am, it was a really wonderful section for all these days, and I have learned a few control methodology and new terminology, which I would like to implement in my place. It is really very helpful, ma'am. I really thank for the entire team and the coordinator, and special thanks to the institution also. Thank you.
Thank you so much, sir. Thank you so much for your feedback. there is someone for giving the feedback? We are getting some feedback in the chat box too. Thank you so much for your positive feedbacks. This is our 4th faculty development program. So we are trying to incorporate international as well as our national experts on this who are working in advanced topics in control system. And this is a platform for us to interact, and we can also further collaborate with each other for our future endeavors too. So this is the objective of our FDP. Thank you so much for all the feedbacks. Thank you so much for the active participation. Before concluding, I would like to inform you something like we are pleased to inform you about the upcoming Engg-KKWIEER Expo 2026 national level working model contest and project exhibition, which is scheduled on 27th and 28th March 2026 at KKWIEER Institute of Engineering, Education and Research, Nasik. This prestigious national level platform offers an excellent opportunity for you and your students to showcase innovative projects, their working models, and the research-based ideas to a wider academic and industrial audience. So we sincerely invite all the faculty members and your student project for this expo and making this event a proud display of our department's creativity, technical excellence, and innovation. So the detailed brochure and other registration details, guidelines will be shared shortly through the email and your WhatsApp. Please encourage your students, your student projects to participate in this project competition. And we are inviting all of you to our college for this particular event. So we will share the details soon. Thank you for listening us. And one more thing, we have our feedback links and our quiz for these sessions. We will share those feedback and quiz shortly through the WhatsApp group. I request all the participants to kindly complete that, and the certificates for the participation will be shared within 1 week. So kindly wait for the same. Let me conclude by delivering the vote of thanks. Over the past 6 days, this FDP has been a wonderful journey for our learning, interaction, the reflections, and our intellectual growth. Each session's added depth to our knowledge and broadened our perspective. First and foremost, I express our heartfelt gratitude to all the distinguished resource persons who generously shared their expertise, research insights, and practical experiences with us. We have few of our experts in these sessions too. Thank you so much, all the experts, for sharing your valuable insight with us. Your sessions are not just informative, but it is inspiring. It provides us a clarity, depth, and a real world relevance to all the discussions, and have made this FDP immensely valuable. I sincerely thank our respected principal and management for their continuous engagement and support in organizing this program. Their vision toward academic excellence and research driven learning made this FDP successful one. Then now I would specially like to express our deepest gratitude to Dr. R.K. Munje, our respected HOD, whose constant guidance, his seamless coordination, and strong support, that was the backbone of this FDP, without which this enriching journey would not have been possible. Unfortunately, he is not able to be present in this conclusion session, as we are having some event which is going on in the college institute level. But whatever support he had done, whatever effort he had put behind this FDP is really priceless. Thank you so much, Munje sir, for his continuous support. Then I would like to sincerely acknowledge Ms. Ashwini Patil, whose constant support, her dedicated assistance, and her tireless coordination behind the scenes played a crucial role in this smooth and successful conduction of this international session. Then I would like to thank all the participants for your enthusiastic involvement, your meaningful questions, and active engagement throughout the program. This FDP becomes successful not just because of the speakers, but also the committed and sincere learners. As we conclude today, let's carry forward the knowledge, the ideas, and inspiration gained here into our classrooms, in our research work, and our professional practices. With great gratitude and appreciation to everyone who contributed to this successful program, I formally propose a vote of thanks. Thank you so much. Thank you so much for all your kind support and participation. With that, we are concluding this faculty development program, and thank you everyone for having you with us for the last 6 days of our journey.